Okay, we are going to start talking about molar masses now. Remember, the mole is the one thing on the periodic table that relates all the elements together. Well, molar mass relates them by mass itself, by the grams. For instance, sulfur, which is here on the periodic table, 32.07, what that really means is that for every 6.022 times 10 to the 23rd atoms of sulfur, it's going to weigh approximately 32.07 grams. That's what the molar mass is telling us. So it can tell us of individual elements, or if we want to do a whole compound, it can tell us the mass of that many molecules of the entire compound. But either way, it's relating each one of these numbers to moles. So 1 mole of sulfur is 107.9 grams. 1 mole of carbon is 12.0 grams. 1 mole of sulfur is 32.1 grams. You can round it up to the 10th place, or you can round it up to the 100th place. It's up to you. But I wouldn't go past more than the 100th place, because otherwise that just gets tedious for no reason. So, let's take a minute to practice. We are looking for the molar mass of each of the elements. So, potassium atoms, because they're individuals. So we look for potassium. Here's potassium. This is the molar mass of potassium, 39.1. That means that this is going to be 39.1 grams. 10. So we look for 10. Here's 10. 118.69. So that becomes 118.7 grams. Finally, calcium. Calcium is right here, 40.08. That means it's 40.1 grams. So essentially all we're really doing is looking on the periodic table and looking for the molar mass. There's typically 2 numbers on the periodic table. The first one is telling you how many protons there are, and that's always 100% of the time going to be the smaller whole number on the box. The bottom number is typically not going to be a whole number. Sometimes there are, but usually it's rounded off somewhere. And that's going to be the atomic mass. That's the average of all the isotopes added together. So, not only can you find out individual atoms like carbon, hydrogen, or oxygen, we can find the whole thing as a molecule. So how we do that is we look at each of the elements individually and then combine them. We have carbon, hydrogen, and oxygen. We have 2 carbon. We have 6 hydrogen. There's no number here, which means that there's a 1 oxygen. So we look back on the periodic table and we look for carbon. It's right here, 12.01. So we say 12.0. So 2 times 12.0, because there's 2 of them, 24. Hydrogen. It's right here, 1.0079, which rounds off to be 1.0. 6 times 1.0 is 6. Finally, oxygen is right here, 15.9994. That rounds up to 16.0. So 24 plus 6 plus 16, 46. 16.0 grams, and that's going to equal 1 mole of this whole compound. So if we have 2 moles of the carbon, 6 moles of the hydrogen, and 1 mole of the oxygen, those things combined is the molar mass of that compound itself. Let's try a couple more. K2O and AlOH3. This is potassium oxide, by the way. And this is aluminum hydroxide. If you do not remember how to name things, I would strongly suggest going back and reviewing that, because that will be important. Alright, so let's look at potassium oxide. We have K, and we have O. Look at the compound itself. K, we have 2 of them. Oxygen, there's no number here, so that means it's automatically a 1. So we have 1 oxygen. That's where those numbers came from. Now to get the next numbers, we need to look on the periodic table. So here's our periodic table. Potassium is here. 39.1. So we come back over here, and we say it's 39.1 grams. Then oxygen, right here, that's 16.0 grams. That means this is 78.2 and 16.0. Add those together, and that comes out to be 94.2 grams is equal to 1 mole of K2O. You could also write that 94.2 grams per mole of K2O. Alright, let's take a look at the next one. We have aluminum, oxygen, and hydrogen. So notice that this is in parentheses. That means that this 3 on the outside goes to both the O and the H. So that means we have 3 sets of OH. But there's no number here, which means we have a 1. There's no number here, so that's a 1. So it's 3 times 1 for 3. An invisible 1 here as well. 3 times 1 is 3. Now we go back to our periodic table and we look for aluminum. Aluminum is right here with a molar mass of 26.98, which rounds up to 27.0. Oxygen is right here again, 15.994, and that rounds up to 16. And finally, hydrogen, which is right here. It's also over here on the left-hand side, and that rounds up to 1.0. So 1 times 27 is 27. 3 times 16 is 48. And 3 times 1 is 3. We're going to add all that together, and that comes out to be 78.0 grams per mole of aluminum hydroxide. Okay, we're going to try another one for Prozac, specifically for medicine related. It is a really big compound. C17H18F3NO is an antidepressant that inhibits the uptake of serotonin by the brain. What's the molar mass of Prozac? So that means that we need to break this compound down. We have carbon, hydrogen, fluorine, nitrogen, and oxygen. We have 17 carbon, 18 hydrogen, 3 fluorine, no number, so that means 1, nitrogen, no number, so that means 1, oxygen. That means we have to look for all these elements on the periodic table. So if we look here, the first one was carbon. It's 12.011, which means it runs off to 12.0. Hydrogen is right over here, 1.0079. That rounds off to 1.0. Fluorine, which is right here, 18.99, which rounds off to 19.0. Nitrogen, can't really see it now, but that says 14.00, which means that's 14.0. And oxygen, which is right here. Once again, you can't really see it. I've been writing too much. It says 15.994, which means that's 16.0. So, we're going to take 17 times 12, comes out to be 204.0. 18 times 1 is 18.0. 3 times 19 is 57.0. That's going to be 14.0, and that's going to be 16.0. It doesn't matter how complex the compound is, the method is always the same. So it would be 207 plus 18 plus 57 plus 14 plus 16. That comes out to be 312.0 grams per mole of that big compound for the antidepressant, for Prozac. That was really sloppy. Alright, now, you notice that I kept saying grams per mole, or that equals 1 mole? Well, just like with all other conversions, we can use those as conversion factors, which means we can set them up as fractions just like we were doing in the previous chapters. So if we take a look at this, we have 737 grams of sodium. You can barely see it right there, sodium chloride, in this box. We want to know how many moles that is. So we have 737 grams of sodium chloride. In order to go from grams to moles, we need to figure out the molar mass to do that, because the molar mass is grams per mole. So before we do anything else, we need to figure out our conversion factor. So that means we need to look in the periodic table for sodium and chlorine. Sodium, there's no number here, so it's a 1. Chlorine, there's no number here, so it's another 1. Sodium on the periodic table is right here, 22.98, which means it is 23. Chlorine is right here, 35.453, which means 35.5. So that means 23.0 and 35.5. We're going to add those together. That comes out to be 58.5 grams. So that means our conversion factor is then going to be 58.5 grams is equal to 1 mole of sodium chloride. So if I have 737 grams over 1, we we have grams on the top, that means we want to put it on the bottom. Here's grams, 58.5. That's equal to 1 mole. Grams cancel, so 737 divided by 58.5. That comes out to be 12.6 moles of sodium chloride. Notice that all we did was figure out what the molar mass of the compound was, and then that gave us our conversion factor to get from grams to moles. Okay, let's try another one. Allyl sulfide, C6H10S, is a compound that has the odor of garlic. How many moles of C6H10S are in 225 grams? So we have C6H10S, we have 225 grams of it, and we were trying to get to moles. We're going from grams to moles. Whenever you go to grams to moles or back again, you're going to want to find the molar mass every single time, which means we need to figure out the molar mass of this compound. So CHS. We have 6 carbons, 10 hydrogens, and 1 sulfur. So if we look here, our carbon is right here, 12.01, which makes it 12.0. Hydrogen is next, on the left-hand side, 1.00, which makes it 1.0. And then sulfur is our last one, and that is here, 32.06, which makes it 32.1. So 6 times 12 gives us 72.0. 10 times 1 gives us 10.0. And 1 times 32.1 is 32.1. We're going to add those together. That comes out to be 114.1 grams of C6H10S is equal to 1 mole of C6H10S. And that's going to be our conversion factor now. So we're going to take this 225 grams of it. We're going to put that over 1, because that's going to be our starting number. We have grams on top, which means we want to put grams on the bottom. We're left on our conversion factor, and we're going to find that it's 114.1. That is equal to 1 mole. Grams cancel, and we're left over with moles. So 225 divided by 114.1. And that comes out to be 1.97 moles. Notice that there were 3 significant figures. There's 3 significant figures here. So as a summary, let's take a look at a comparison here. And either way, to go from grams to moles, grams of one to moles of the other. Doesn't matter if you're looking for elements or compounds. You're going to need the molar mass to do that. In either scenario, if you're looking at elements or compounds, in order to get into atoms or molecules, you're going to use Avogadro's number. Now, if you happen to have a compound and you're looking for specific elements or for specific atoms, that's when you're going to use the subscripts. That's the only time you ever use the subscripts. That is the general idea of molar mass. I suggest practicing in it. and good luck.